Hello, everybody. In today's seminar, we will see how the detectors work and the data acquisition. So I will deal with the neutron detectors and David Portinari will deal with the data acquisition. So first of all, I will introduce the topic with the different families of detectors. Then I will focus on the widely used detectors at the ILL, so the helium-3 detector. I will present its operation, characteristics, and limits. We will see then the multi-grid detector, which will be mainly used at the ESS in Sweden before to conclude. Okay, so let's start. So during the previous seminar, we saw the neutron sources and guides up to the sample. The neutrons are then scattered, and we have to detect them and to count them. And this is the topic of this seminar. So there are two families of detectors, the integration sensors and the counters. So for the integration sensor, during an integration time, the detector is collecting all the charges arriving on it. So for example, there are CCD sensor and image plate. For the counters, we count each neutron one by one. We analyze each produced signal to determine the nature of the particle. And the idea is to configure the detector to be sensitive only to neutrons. So the first one, so the integration sensor, they allows a better spatial resolution. And so it is used for small samples producing a weak signal. Whereas the counters allows to distinguish all the incident particles and so to detect only the particle of interest, which is the neutron in our case. And so I will deal during this seminar with counters. So to detect something, we produce a detectable current through electrostatic interaction. But neutrons, as we know, they are electrically neutral particles. Thereby, we need neutrons converters. To convert the neutron into charged particle. So the neutron is here absorbed by the target material, which is the converter. So for example, the helium-3, and emitting secondary particles, for example, proton, alpha particles, beta particle, photon, etc. So for example, with helium-3, during the nuclear reaction, a tritium and a proton are produced with some energy which correspond to the reaction energy. And there are other possible reactions using lithium-6, bor-10, or uranium-235. And so all of these reactions have a certain probability to take place. And we saw it during the previous seminars. It is linked to the capture cross-section, which correspond to the effective area represented by the nucleus to an incident neutron for absorption. And the capture cross-section is then the probability of capture between an incident neutron and the target nucleus. And the helium-3 and the bor-10 have a large cross-section compared to lithium-6 and uranium-235. And this is why we will focus on the reaction between neutron and respectively helium-3 and bor-10 during this seminar. So we can also note that the cross-section, which is represented as a function of the neutron energy, so the capture cross-section is varying linearly with the inverse of the neutron energy in the region of interest. So for thermal neutron, which have an energy which is around 25 milli-electron volts. Okay, so now I will deal with the helium-3 detectors. So the easiest way to present the helium-3 detector is to consider a hollow cylinder which is filled with helium-3 gas, and there is a wire inside. And we apply a voltage between them, between the wire and the cylinder, and there is an electric field which appears and which have this expression where V is the applied voltage, R is the radius, and B and A are the radius of respectively the cylinder and of the wire. And the polarity of the applied voltage is chosen so that the electrons are attracted to the wire, which is then the anode, and so the cylinder is the cathode. And the electric field is maximum on the anode surface, and it is equal to 5 times 10 power 6 volt per meter, and it is equal to 0 on the surface of the cathode. So now let's see how it works. So when a neutron arrives in the gas filled cavity, there is a certain probability that the neutron meets a gas molecule. As we saw it earlier, it is linked to the capture cross-section. And so this reaction takes place and produces a tritium and a proton. And these two particles have a certain energy, whereas the sum, so the energy of the proton plus the energy of the tritium, it is equal to the reaction energy, so to the 764 kiloelectronvolt. And therefore, on the path of the proton and of the tritium, there is a creation of electrons-ions pair. So the electrons are represented in red, and the ions are represented in orange. And so the electrons, negatively charged, are attracted to the anode, which is positively charged. Okay, and so they drift to the anode until they reach a certain region of space. So let's go back to the representation of the electric field. So when the electric field is higher than a certain value, which corresponds to epsilon, so in the region of space between A and the epsilon, so the electric field is higher than epsilon. And so I represented here the cylinder associated to this region of space. So in this region of space, the electrons have acquired a sufficient drift velocity. So we have to keep in mind that primary electrons drift to the anode, and they are accelerated as they approach the anode because the electric field is very intense, and they will accelerate the electrons. And then the electron have acquired a sufficient energy to ionize the neutral gas molecule. And then the primary electron will produce a secondary electron-ion pair, and again and again. And so this is what we call the avalanche phenomenon. So a primary electron will produce 100 secondary electrons. And so all the secondary electrons produced are collected on the anode, and the produced ions migrate toward the anode. And so during the motion of the charges, an electric current appears, and its integration gives the total charge. And so by measuring this charge, Q, we can deduce the reaction energy because the charge is proportional to the energy. And so if this energy is equal to the 764 kiloelectronvolt, then we can know the nature of the incident particle, which is indeed a neutron. So to make a short recap, we use helium-3 to convert the neutrons into charged particles. Then primary electrons are created along the track of the proton and of the tritium. And these electrons are going to be accelerated as they approach the anode. And they are going to acquire a sufficient energy to ionize the gas, and so to produce secondary electrons. And during the motion of all the created charges towards their respective electrode, a detectable current appears, and by integrating it, we can have access to the total charge. But during the collision, the electron could also not ionize the gas molecule, but excite it. And during the de-excitement of the molecule, the gas molecule will pass from an excited state to the ground state by emitting a photon. And this photon could produce new electrons by interaction with photosensitive elements, such as the metal of the cathode. And so these new electrons will have to drift from the cathode to the anode for a long time, and they could create a new photon, which will create new electrons, and again and again. And so we're going to use quencher gas, so for example CO2, to avoid the self-sustaining avalanche phenomenon. And besides, we will also use argon, which have a higher stopping power than helium-3, and which will decrease the size of the primary track of the particle, and so improve the spatial resolution which will improve the spatial resolution by better localization the site of interaction between the neutron and the helium-3 molecule. Okay, so we saw the operation of the helium-3 detector. Now we will see an important notion in the development of a detector, which is the energy distribution of the signals. So it's the energy distribution. So it corresponds to the energy spectrum of a detector for an energy source, and so to the number of events that have an energy between E and E plus D. So it's just the energy spectrum of a detector for a sources. And so for a helium-3 detector, we expect this kind of distribution with a peak for small energy, which corresponds to the gamma, because the gamma produces a very fast electron, very penetrating, and which deposits very little energy. And the other part of the distribution corresponds to the neutron. And to understand the shape of the distribution, we have to study the nuclear reaction. So to produce the tritium and the proton, there is a collision between a thermal neutron and a helium-3 molecule. And both have a thermal motion. So we assume that the linear momentum of the center of mass of the helium-3 and of the neutron is equal to 0. And according to the collision theory, the momentum is conserved, and so the momentum of the proton plus the momentum of the tritium is equal to 0 from vectors. And so if we have no vectors, there is this expression. So where the momentum of the tritium is equal to the momentum of the proton. And we can replace the velocity by the kinetic energy. And if we isolate the energy of the proton and replace the energy of the tritium with this relationship, where Q is equal to the reaction energy, to the 764 kiloelectronvolts, and EP is the energy of the proton, and it is the energy of the tritium, then we can have this expression, and we can isolate the proton energy, and we have this final expression. And we know the mass and the reaction energy. And so we can deduce the energy of the proton and of the tritium. And so if we go back to the distribution, let's consider the first case. So I represented here the detectors with the cathode and the anode. And so there is a collision between a neutron and the helium-3 molecule. And so there is a proton and a tritium which are produced. And as we can see here, the track is not fully inside the detector. And so we will measure all the energy of the tritium, so all the 191 kiloelectronvolt, but only a part of the proton energy. So only a part of the 573 kiloelectronvolt. And so we are in this region of space. We are measuring all the energy of the tritium, but only a part of the energy of the proton. So there is another case where we are measuring all the energy of the proton, but only a part of the energy of the tritium. And so we are measuring the 573 kiloelectronvolt plus a fraction of the energy of the tritium, so of the 191 kiloelectronvolt. And so we are in this region of space. And this is what we call the wall effect. And there is the last case where all the track is inside the detector. And so we are measuring a full peak energy with a peak of 764 kiloelectronvolt. Okay, so now that we understand this distribution, we have to keep in mind the problem, which is to count all and only the neutrons. And so we must set a threshold to distinguish gamma from the neutrons. And so we will put this threshold here in the valley. because there is a good distinction between the gamma and the neutron. And so what does it mean? It means that if a particle deposits an energy higher than the threshold energy, then we will count the particle because we know that this is not a gamma but a neutron. And so this is why we count only neutrons, because we fix a threshold. Okay, so we saw that to count a neutron, the deposited energy must be higher than the threshold energy. But even if this condition is met, we will not be able to detect all the neutrons, because in all detector systems, there will be a minimum amount of time that must separate two events in order that they be recorded as two separate pulses. And this limiting time depends in part of the associated electronics. And this is David Portinari that will deal with this later. And this minimum time separation is usually called the dead time. So the dead time, which corresponds to the processing time of the current signal produced by the charges. So for example, imagine that here are all the events that happen in the detector. So at the time t1, there is a particle which arrives on the detectors, and we will be able to measure it. So there is two types of detectors, parallelizable and non-parallelizable, and I will come back on this later. But for the first neutron, there is no problem. We can measure it. For the second one, T2 minus T1 is higher than the dead time, so we can measure it for both detectors. But for the third one, because T3 minus T2 is lower than the dead time, so we are not going to be able to measure the third neutron. And for the fourth neutrons, we have to, there is two cases possible. There is two possible cases. So for the parallelizable, the event that occurs during the dead period, even if they are not counted, they will extend the dead time after the dead event, which means that for the fourth neutron, we have to, the time that we're going to use is T4 minus T3. And so we can see that T4 minus T3 is lower than 2, so we are not going to detect the first neutron. But for the non-parallelizable detector, the events that occur during the dead period are lost and have no effect on the behavior of the detector, which means that we're going to consider T2. And so T4 minus T2 is higher than 2, so we are going to detect the fourth neutron. So for the parallelizable detector, we will count only 2 neutrons out of 4 against 3 out of 4 for the non-parallelizable detectors. And there is a formula for each type of detectors. So knowing the measure, so the recorded count rate, M, we can have access to the real count rate. So for example, here M is equal to 2 and N is equal to 4. And so we can have access to N knowing the recorded count rate. Okay, so we will deal now with the efficiency of the helium-3 detector. But before that, let's do a quick reminder on the Beer-Lambert law. So an incident beam passes through an absorbing medium, and then the output intensity is equal to the incident intensity time a decreasing exponential. And this decreasing exponential depends on the absorption coefficient. And the efficiency is the ratio of the two intensity, and so it is equal to the absorption coefficient. So for the detector now, we want the neutrons beam to passes through the wall of the detectors, but and we want that the neutron to be stopped by the gas. And so the efficiency corresponds to the probability of going through the detector window, and so it corresponds to the decreasing exponential as for the Beer-Lambert law, times the probability of being stopped by the gas, which correspond to 1 minus the probability of going through the gas. And so we have this expression, and we can note that the absorption coefficient of the gas is equal to the capture cross-section times the density of the gas. Okay, so now that we saw how to count the neutrons and the efficiency of the detector, there is one last very important notion, which is the detection of the position of the impact between the neutron and the helium-3 detectors. And there are two ways to localize the impact site. So the use of position-sensitive detector, so PSD tubes, or the use of multi-wires proportional chambers, MWPC. So let's see how works PSD tubes. So the particle path is represented in red. And from the point of collision, which is here, the intensity separates between the different connection of the electrical circuit according to the electricity laws. And so we can measure a current here and a current here. And we can integrate it. And so we have access to the charge, QA and QB. And then we're going to be able to localize the collision site, so X, which is a ratio of the charge times L, and L represents the length of the tube. And so this is why PSD tubes is a charge division detector. And there is multi-wires proportional chambers. And so multi-wire MWPC is a discrimination detector, which means that it counts with 0 and 1. So 0 means that the threshold is not exceeded, and so that the particle is not a neutron, but another particle, so such as a gamma, and so we are not taking care of gamma, so it do not interest us. And 1 means that the threshold is exceeded, and so that the particle is a neutron, and so that we want to localize the impact site. And so here the particle path is represented in red, and we are measuring all the signals. So 1 means that this is a neutron because the threshold energy is exceeded, and if there is a 0, it means that there is no neutrons. And so we can make a coincidence of the tracks, of all the tracks. And so we will be able to localize the place of collision. Only if all the coincidences are made at the same times, which means that all these phenomena are linked to the arrival of the same neutron. Okay, and all are used at the ILL. So PSD tubes are used on D22. So there are 100 to 28 PSD tubes, which covering 1 meter of area. So one tube is a 1D detector, and 128 tubes is a 2D detector. And the diameter of the tube is around 8 millimeters. So it's a good spatial resolution in 1D, and there is a good efficiency. And there is multi-wires proportional chambers on D19, so with a very large angle, and there is a good resolution, and so a good efficiency, which is around 80%. But helium-3 detector requires a large amount of helium-3. And however, since the 2009 crisis, helium-3 has become very rare and very expensive. For example, for a typical detector, it requires 1,000 liters of helium-3, which costs close to 6 million euros. And so a new detector was then developed here at the ILL, and this is a boron multi-grid detector. And so the operation is very close to the helium-3 detector. So the detector no longer uses helium-3, but layers of boron. And so the detector is represented here, and there is a picture of the representation of the detector. So it is composed of a multi-grid detector, which correspond to the cathode, and there is a wire inside, and which is the anode. And so this is due to the polarity of the applied voltage as the same way as for the helium-3 detector. And so there is an electric field which is present, which is very high close to the anode, and which is equal to 0 on the anode. And so the grid is covered with boron. So if we zoom on the wall, there is aluminum, which is a substrate, which is transparent to neutrons, and so which induces very little absorption. There is an boron deposit, so which is the converter of the neutron in this nuclear reaction. And there is a gas, so the stop gas, so the argon, and the quencher gas to absorb photon. And so in the same way as for the helium-3 detector, during the first collision between the neutron and the boron, there is a creation of the lithium and the particle alpha, the alpha particle, and along the track there is charges, so the electrons and the associated ions. And so these charges are attracted to their respective electrode, so to the anode for the electrons and to the cathode for the ions. And during the motion of these charges, the electrons are going to be accelerated, and so they are going to ionize. And so they are going to ionize the gas and to create new electrons ions pair. So secondary particles are produced, and the motion of all the created charges induces a current, and by integrating it, we can obtain the total charge. And so to have a good efficiency, we need layer of a sufficient thickness, but not too big, otherwise the neutron will be absorbed in depth, and the particle created will ionize the solid, but which will never leave the solid to go into the gas. And so we are not going to be measure a detectable current because we are not going to produce secondary electrons. And this is why we are going to use multi-layers. So if we use a single grid, the efficiency is very small, so around 5%. And for a multi-grid, the efficiency is really high, around 80%. Okay, so to conclude, the neutrons are not directly detected, but they are converted into charged particle through the nuclear reaction with the converter, which is, for example, helium-3 or boron-10. So a high electric field is needed to produce enough secondary electrons during the avalanche phenomenon, and so to have a detectable current. And so we are going to integrate this current to have access to the total charge, Q, which is proportional to the energy E deposited into the gas. And if this energy is higher than the threshold energy, which make a distinction between the gamma and the neutrons, then we can conclude that the incident particle is a neutron. And we can have access to the position of the collision by using a charge division detector or a discrimination detector. So I would like to thank all of you for your attention, and I would like to thank David Portinari because he answering my questions, and Bruno Gerard and Paolo Muti for their time. Okay.